So for day 4, we're going to concentrate on applying the derivative rules to answer higher order questions like finding horizontal tangents, locations of those, and then we're going to also use it to look at functions and their derivatives from a tabular perspective. In other words, a table of values. Which also could be a graph of values as well. And so let's look at this first example here. It says find the horizontal tangents of x to the 4th minus 2x squared plus 2. So first let's find, when we talk about horizontal tangents, we're talking about horizontal being 0 slope. So we're looking at the derivative here, and so when I say derivative, you think slope. So the derivative is bring down the 4, reduce the power to a 3, bring down the 2, multiply it by 2, get a 4, reduce the power to 1, derivative of a constant is 0. So here's the expression for the derivative, and then what we're going to do is, if this is the derivative, or this is the slope of the graph, then we want to set that equal to 0 because we want to have a horizontal slope or a horizontal tangent. So we're going to go ahead and set that equal to 0, factor, we can divide out the 4, then we're going to go ahead and factor out an x, and then we're going to continue to factor out this difference of perfect squares. So we end up having x times x plus 1 times x minus 1 equals 0. So our 0 product property says that if x is 0, this whole thing is 0. If x is negative 1, that makes this 0, that makes this whole thing 0. And if x is a 1, that makes this 0, which makes this whole thing 0. So our locations of horizontal tangents are these 3 x locations. So let's see what we get in terms of y values, because horizontal tangents are equations y equals something. Let's see what y values we get when we plug in these 3 x values. So when we plug in 0 to here, we get 0 minus 0 plus 2. So one horizontal tangent, remember horizontal tangents have the form of y equals. One horizontal tangent is that y equals 2. When we're talking about horizontal tangents, we expect to see an equation for a line because horizontal tangents are lines. When we plug in negative 1 here, we get negative 1 minus 2 plus 2, which is y equals, not negative 1, we get 1 because negative 1 to the 4th power is 1. 1 minus 2 plus 2, so y equals 1 is another horizontal tangent line. And then when we plug in positive 1, we get 1 minus 2 plus 2. So we get the same equation. So the last two here are actually duplicates of the same line. So let's take a look at what that means. So we know we have an even function. That means we have the highest power is even. So we're only going to get 2 horizontal tangents here. So let's take a look at the function here. Here's our function. And here's that horizontal tangent y equals 2. And here's that horizontal tangent y equals 1. So if you notice that horizontal tangent y equals 1 touches the curve at x equals negative 1 and x equals positive 1. So it's a single line that happens to have 2 points of tangency because of the shape of this curve, the symmetry of that curve. So if we graph the derivative, we notice that first of all, if we have a degree of 4, our derivative is a degree of 3. So instead of down, up, that's a 4th degree polynomial, we have up, down, up. That's a 3rd degree polynomial. Also notice that the value of the derivative is 0 at negative 1, right? These were the zeros we found. The horizontal points of, the horizontal tangent lines have slope of 0. So here's our slope, right? Our derivative is our slope. So we have a value of 0 here. We have a horizontal tangent here, so we have a value of the derivative of 0 here. And a horizontal tangent here, which means the value of the derivative is 0 here. So looking at this, let's take a look at this valley on the left here. as we approach it, we have negative slope in our function. If we would draw tangent lines, those would all be sloped negative. And so if we notice, that corresponds to negative values for the derivative here. Then we get to 1, the derivative of 0, and then now we have positive slope in this area of the function. So we would have tangent lines that are sloping upward. That represents this positive slope represents this right here. Okay, so we notice that we have a slope of 0 and we have a slope of 0. We have a value of 0 and 0. So our tangent lines, the slope increases to a point, and then the slope starts to decrease back to 0. So the slope increases to a point, and then it decreases back to 0, the slope values or the derivative values. And then in this region, we have negative slopes again. They start at 0 and come back to 0, which means they must get smaller or more negative, and then they must get bigger or less negative. So if we look at the derivative values down here, the derivative values get smaller or more negative, and then there's some maximum negative value here, and numerically that's a minimum, and that corresponds with some location about right here where the tangent line, the slope is going to get as steep as possible, and then it's going to start to flatten out again. So then those negative values get larger and larger until they come back to 0. And then in this region, after this valley, we have positive slope. So the tangent lines are positive here. They're sloping up on the function. So if you notice on the derivative graph here, we have positive values in that location of the graph. So the first derivative is 0 at those 3 points, just to recap that. Okay, so here's a function, and we want to find the derivative. And it's a fraction, so we can actually approach this fraction in 2 different ways. We can do the quotient rule, where we have our pretty complicated expression for the derivative. So let's take a look at that. So we know the quotient rule says take low times the derivative of the high. So the low function is x cubed. The derivative of the high function is 0. Minus high times the derivative of the low. So the high function, the numerator, is 2. Times the derivative of the lower function, the denominator, is 3x squared. All over low squared. So that's low d high minus high d low over low squared. So when we simplify that, we get negative 6x squared over x to the 6th, which if we simplify that a little further, it's negative 6 over x to the 4th. So that's not too bad to use the quotient rule. It's just that the quotient rule sometimes is hard to remember. So the second one is we can use the product rule. So we have to write this as a product, which means bringing the denominator up here. And we can do that using negative powers. So we can rewrite the function as 2 times x to the minus 3. And then now we can go ahead and it's really not even a product rule at this point. It's really more of just a power rule. We bring down the minus 3 and multiply it times 2. That gives us a negative 6. And then we make this 1 smaller, which means we're going farther into the negatives. So the new power is negative 4. So anytime you can rewrite a fraction using negative exponents, sometimes it makes the problems more simple. And of course, negative powers just mean that we can relocate it to in fractional form to the other location, in this case into the denominator. So for this problem, this is either a tabular problem, or we could give you the information in a graph as well. But what we have here is we want to find the derivative y prime. If the derivative of y prime at 2, if and this is to use for products and quotient rules, if the function u is equal to 3, its derivative is equal to negative 4. The function v is equal to 1, and its derivative is 2. So if we think of the definitions or the rules of the product of derivatives and the quotient of derivatives and plug in those values, we can find the value of the derivative of y just using either the table of values or this list of values. Or like I said, we could actually have these values given to you in a graph as well. This would be 2 comma 3, this would be 2 comma negative 4, this would be 2 comma 1 and 2 comma 2 if we would give that to you in a graph for Cartesian coordinates. So let's think about it in this way. If y is a product of the functions of u and b, so we're looking at using the product rule here, then what's the derivative of y? So we know that the product rule says if we have a product of two functions, we find the derivative by taking the first times the derivative of the second, plus the second times the derivative of the first. And we've written that in previous lessons like that, uv prime plus vu prime. So we're going to go ahead then, we have all these values up here. So we're going to go ahead and plug those in. So if we look at this, the value of function u is 3. So we put the 3 in there. The value of the derivative of v is over here. It's 2. So 3 times 2. The value of function v is 1. So we substitute 1 in there. And the value of the derivative of u, or u prime, is negative 4. So here's the product rule using those values for functions and derivatives. And then after we evaluate this expression, we have 6 minus 4, which is 2. We could also use these values and give you the question of what would be the derivative be if y is defined as the quotient of u divided by v. So in this case, we're talking about the quotient of a function or using the quotient rule. So we know the quotient rule looks like this. So if you remember, this is low d high minus high d low over low squared. Okay, and we've written that like this, as vu prime minus uv prime over v squared. And again, we have all of these values. So substituting this in, it looks like the value of function v is 1. The value of the derivative u prime is 4. The value of function u is 3. There it is. The value of the derivative of v is 2. There it is. And then the function v is 1. And we're going to square that. So evaluating this, it looks like we have minus 4 minus 6. It's minus 10 divided by 1, which is negative 10. So we can use a tabular approach or a list of values here, or a graphical approach if we had these graphed on a XY graph, to find the values of the derivatives using the product and the quotient rule. So for higher order derivatives, in other words, when we take the derivative, we get another function. We can take the derivative again and get another function again. So y prime we call the first derivative with respect to x, because y prime is the first time you take the derivative. Y double prime is the second derivative. Y double prime, remember our new language? So really what we're doing is we're taking the derivative of a derivative. And so here's a couple different notations. We can call this dy prime dx. We can call it y double prime. We can call it d dx, dy dx. Or we can call it the second derivative of y with respect to x. And we can take the derivative again. And we can keep taking derivatives of things until we reduce all of the powers and we end up with 0. So this is y triple prime, and it's dy double prime dx. It's the third derivative. We also kind of call this the jerk. And this is kind of a physics sort of thing, where if we start with a function y, we usually consider that position, and then y prime, we consider the instantaneous rate of change of position, so we call that velocity. Then y double prime is acceleration, and y triple prime is the change in acceleration. And the change in acceleration is called jerk. If you think about driving a car and you change your acceleration drastically, in other words, you push down on the gas pedal really drastically, or you push on the brake really drastically and you start to jerk yourself around the car. That's your acceleration changing. And then we can go on and on. After triple prime, we usually start putting instead of the little hash marks, we usually start putting a number that represents the derivative, the number of times we've taken the derivative, in parentheses. The reason why we use the parentheses is because we don't want to mistake this for a power. So this is d dx of y triple prime. We're taking the derivative of y triple prime, so this is the fourth derivative. So I kind of alluded to what the higher order derivatives are used for. We use them a lot in motion and in physics, and we'll kind of touch more on that later in the chapter. So at this point, you should be able to complete day 4 homework. So go ahead and complete that in WebAssign, and go back and make sure your days 2 and 3 are also completed. And then next time we meet, I'll also have a Blackboard quiz ready for you if you want to take a Blackboard quiz to practice those skills and see where you stand on proficiency.